Welcome everyone. Let me share my slide deck real quick here. All right. Hello everyone. I'm Sean Feldman. I've been involved with messaging services and Azure Service Bus specifically for quite a few years, helping clients to build their systems in Azure, as well as part of my main work focus and activity in the last 5 years, 6 now, I guess, was as an MVP, actively contributed to the Azure Service Bus SDK, track 1 and track 2, which is the latest version of the Azure Service Bus .NET SDK, which we will see later in the presentation. So without further ado, let's start our presentation. All right. So what we'll cover today. First, we'll look into what's been a traditional approach to build software and how that has evolved until recent days, often introducing similar changes into the cloud era as well. This is going to be a brief couple of slides. Then we'll have a quick look at what makes Azure Service Bus a very solid enterprise messaging service of a choice. After that, we'll follow with a review of some of the messaging concepts supported by Azure Service Bus, but unfortunately not everything. For that, we'd need a whole another webinar or a few if you wish, just to cover everything that Azure Service Bus has to offer. And after that, a few conclusions to wrap it up with questions and hopefully answers that I will provide to you. All right, so to understand the challenges, let's quickly look at the early days and how a simple system or an application would be built back in the day. With that, back in the days, an application could be running on something that is fairly simple. For example, a single server that would have all the necessary dependencies deployed to it as well. No latency, no communication gaps, everything running on the same machine, nothing to worry about. Everything is local, happy days. With hardware prices becoming more and more affordable, the system could leverage multiple servers and not just a single machine. The most common scenario that we could talk about is a web application, where the web server and the database server would be a very standard unit of deployment, with potentially another server for backend processing, which would entail a more sophisticated design back in the days. And with hardware virtualization, it also became much easier to introduce scaling. Running web server, for example, with more than just a single node or more than just a single instance, allowing to handle better load on the web app. So for example, when there's a sale, promotion, more customers potentially visiting the web application, and it would be able to handle those requests as opposed with multiple instances as opposed to a single instance that would choke because of the load. But scaling out web application demanded also scaling up the database, right? And scaling out and in allows handling, while it allows handling more web requests, but all those requests, unfortunately, still needed to end up talking to the same database. While the data could be sharded, in most typical systems, that's not necessary, and also it's not a trivial solution, sharding your database. So with scaled out web application, database became somewhat of a bottleneck, and it needed to keep up with the web request. The traditional approach on premises would be to scale that database up, but having a beefier and stronger machine with more requests would also mean more expensive solution, right? You would have to swap out the hardware or provision new hardware, whatever it is. And definitely a problem if we want to be able to handle spikes without necessarily paying for the cost of that scaled up database. But we are living in modern days, and we have cloud to the rescue. But more and more enterprises are adopting the cloud to utilize those resources and unprecedented elasticity that it offers that wasn't possible on premises. And cloud environments make scaling simple and easy, but doesn't solve the same problem of scaling in and out that is cheap, but scaling up and down that is very expensive, still very expensive and not trivial. For example, going back to our canonical example of web application, does everything go into the database has to be executed while a web request is on hold? Not only that, the more use the application gets, the worse those response times will be getting if we're waiting for the SQL Server. And we don't want to constantly scale up and down the database. Not only it's inefficient, it's also, well, expensive, right? The whole idea of the cloud environment was to save on some of that cost, at least one of the ideas. So the database should really keep up with the web application, and the way to achieve that is by using very old concept, which is called queues. And the idea behind that is that queues help with leveraging the load and removing temporal coupling between the web application and the backend, allowing to register work items that need to be processed reliably and handle it at a pace that the resource performing the work on the backend can go through. In our case, the database does not need to be scaled up just to handle a spike of users using the web application, right? So Black Friday sale or whatever it is, we don't necessarily need to beef up the SQL Server just to handle all those. And the web application doesn't need to wait for the database to complete in order to return back to the user. So let's look at a real world example that everyone knows, but not necessarily paying attention to what's happening, because that's exactly what's happening with Amazon orders. An Amazon customer submits an order and gets a response back, notifying the customer that their order has been accepted. It doesn't mean that the order has been completed. The order was not processed right away. Rather, it was in queue, right? It's a request item that has been registered. I'll call it a message. When processing system, let's call it backend, gets to that order request, it processes it, writes it to the database on its own pace, and only after that sends the customer an order confirmation indicating that the order has been received and is now processed. And if you think about this, what happened here is we turned a synchronous workflow or synchronous process into asynchronous. And by doing so, we allowed ourselves to introduce the queuing between the web application and the backend, or the processing part of the system, right? To break that temporal coupling and ensure that we don't have to keep the SQL and the backend up to speed with the web application, and each one of them can work independently. There are also other benefits we'll cover later in the presentation. So when an application is a system, there are multiple players. And those players are often called services that interact with each other. Inter-system dependency is becoming a serious issue due to temporal coupling. Each communication relies solely on non-reliable mechanisms such as REST and HTTP, right? I mean, if you go back to the days of WCF, for example, in .NET, you also know that of web services, if you wish, that a lot of times the entire system can be brought down by just taking one of those services offline. And that's another thing that queues or messaging can help us with. So the solution kind of becomes obvious, all good messaging, but not just queues. Messaging is much more than queues, and Azure Service Bus offers much more than queues and a lot of concepts that are coming from general messaging. Let's have a look at those features. But before we start digging into the features, why Azure Service Bus? Why is it a good enterprise messaging service, right? As the title of this presentation claims to be. Well, first of all, the service is cloud native messaging service. It is not a broker that was born on premises and then migrated into the cloud. It was cloud first, which means that there are a lot of principles that are implemented with the scale out, with the massive utilization in mind. Second thing, it supports reliable asynchronous message delivery. Okay, the reliable is a very important aspect because it's not in memory. It's not something that you're going to get the message or maybe not or lose them. It is 100% reliable. No message will be lost ever, which is extremely important for enterprise type of systems or applications that are being built. At least once delivery of a message is also a very important aspect because there are systems or messaging products, for example, that can provide at most once delivery. They are optimized for performance and speed. Now, Azure Service Bus also can do that, but its primary focus, and I think it shines in the at least once delivery, which we'll talk about as well. Boundaries and trust. Azure Service Bus operates on a unit called namespace. And the access to the namespace allows access to all the queues and other entities, which I will expand later, which is a norm within the corporate boundaries because you don't have to interact with third parties and provide them access. Now, there's also a more granular control that you can establish on the queues within the namespace, but I'm not going to be talking about this in this presentation. And also, Azure Service Bus is better positioned compared to other messaging services when it comes to an enterprise. And I'm not comparing to third parties, I'm comparing actually to the messaging services within Azure, such as Event Grid, Event Hubs. The reason for that is Event Grid is mostly pub/sub notification and more intended between systems interaction or third-party notifications. Event Hubs is more geared towards data ingestion, like IoT scenarios, for example. And Service Bus is the one that is designed for enterprise messaging. I would even say transactional enterprise messaging, and we'll see that in a bit. All right, so what are the concepts that's supported by Azure Service Bus? I'm going to demonstrate some of those concepts using C# and .NET SDK. The SDK is also available for Java and Ruby, I believe Node.js, and probably a few more languages now with the Azure SDK team having coverage for more languages and platforms. Now, the package is Azure Messaging Service Bus version 7 or later. 7.0 is the latest. So that's the latest SDK, and you should probably stick to that one if you're a .NET developer. The reason for that is because most of the optimizations, improvements, bug fixes are targeting that SDK as opposed to the legacy SDKs, and there are two of those. Within the presentation, you will notice in the top right corner a little QR code. The code snippets that I'm using, I'm not doing live coding, not going to waste your time. The QR code is going to take you to the code samples that are available online, which you can pull down and run locally if you wish. That's pretty much it. All right, so the first thing that we're going to talk about is the concept of queues, sending and receiving. In order to get going, we always need to have a client, a Service Bus client. Now, Service Bus client takes either connection string or any other method of authentication, could be managed identity, could be some principal or anything else, any other method of authentication that Azure supports these days. This client serves as a pooling mechanism for connections because Azure Service Bus has a connection to the broker. And unlike most of the cloud services that are HTTP driven or HTTP based, Azure Service Bus is based on AMQP 1.0 protocol, and it's a stateful connection, meaning that your application or your system or service is establishing a connection and continuously talking over that connection. Establishing connection is not cheap. That is why the latest SDK is implementing the connection pooling for you. And every Service Bus client represents a single connection, which you can have senders and receivers over that utilize the same connection. If you need multiple connections, you have to create multiple Service Bus clients. That's the idea. Now, probably in the day and age of serverless, the question is, okay, great, what happens there? Well, there you, in the scenario, for example, Azure Functions, where AWS Lambda is not really relevant, but let's assume you use AWS Lambda with Service Bus, then you do not manage the connections. That is hidden from you. But again, a scale controller for Azure Functions does have a connection that it establishes and keeps that connection live. It's just not visible. So assuming we are in more traditional scenario, or you building your own message pump that continuously receives messages, you establish that connection. You can create senders or receivers using the client. In order to send an actual message, you have to construct Service Bus message type, which accepts string, byte array, memory, whatever it is. And send the message. That's it, as simple as it can be. Now, to receive a message on the other side, again, you're going through the process of creating a Service Bus client, create a receiver, and the receiver has an operation by default, taking no arguments whatsoever, all the defaults. And once the message is received, it has a body, which can be, again, converted back either to a string, to a custom type, deserialized into a custom type, or byte array, memory, whatever it is. So that's simple. Now, when we are sending and receiving messages, sending is not a problem because you just post the message to the broker. But when you receive a message, it's important to indicate how you receive that message. And I said earlier that Azure Service Bus is geared for enterprise. And that means that by default, the message is received in a mode called peak lock. And there is a mode also called receive and delete. And when we create our receivers, if we don't specify anything, by default, it's peak lock. If we want to override it, then we have to provide Service Bus receiver options, stating which mode we want to receive the messages. Now, it's important to understand the two. I'll start from the receive and delete, which is not the default. It means that the moment the broker has sent us the message and we have successfully received it, the message is automatically gone from the broker. That's it. So if our process has failed, our service has crashed, that message is gone from the broker. Quite dangerous operation. Very fast, but has a cost. The default mode, which is peak lock, means the message is stored on the broker. It's locked for a certain period of time. In other words, our receiver is leasing the message for a certain period of time, and no one else can touch that message until our receiver either completes the message or indicates that it doesn't want to complete, or the lease is timing out. So that's important to remember, those two modes. Next, let's look at the payload and metadata. The payload itself, when we're creating Service Bus message, that's the body of the message. But there is also metadata, also known as application properties or headers in general messaging. This is the metadata that can be usually added to the message itself, to the payload. Adding it as simple as accessing message application properties and retrieving it, same thing. It's just a key value collection. Now, why these metadata properties or headers are important? Well, because more advanced messaging features, such as routing, for example, or pub sub, which I will talk in a bit, they rely on the metadata because that metadata allows certain flow control, if you wish, within the broker, and we'll see it in a bit. Next, let's talk about competing consumers for a little bit. The idea behind competing consumers is that I don't have to have a single consumer. I can actually have multiple consumers. So for example, if my queue has spiked in number of messages and I want to process them quicker, I could scale out my processing over the backend, right? And they all talk to the same namespace, to the same queue, and just the messages out of order. There's no order in that scenario. And chew through those messages as quick as possible, right? So that's sometimes, for example, we could have Azure Scaler that is looking at the queue length and decides to scale out the processing unit, or the other way around with the queue length dropping, reducing number of scaled out instances and scaling in. A classical example would be functions. That's exactly what it does. The scale controller looks at several criteria and decides whether to spin up more instances of your function or scale it in. So how normally would we implement these competing consumers if I'm creating my custom services, for example? Well, you need something that retrieves the messages continuously, right? And fetches those. And Azure Service Bus is not based on push, it's based on pulling. So the client has to continuously pull. And that mechanism is usually described as message loop or processor. Its responsibility is to bring the message and provide for processing.
cove.co.